Welcome everyone to this fourth video on an introduction course to functional programming in OCaml. And my name is David Broman, and today I'm going to teach you a little bit about tuples, records, and in particular on algebraic data types that are really useful when you're constructing programs. So it's all about how to construct data and how to deconstruct the data and to use that in programs. And we'll continue to use this REPL editor in a Try OCaml Pro, so you don't need to install anything yet to be able to do some fun coding. Okay, so let's start with tuples. What is a tuple? Well, it's basically a way to compose together data with a fixed number of elements. So we have, for example, an integer, but if we want to have two integers stored together, we can create a pair. And this is a tuple with two elements where both of the elements are of type integer. So if you look at the type signature here, you see that the type is written with a star. It says that this is a tuple with two elements of types int and int. And this particular value was 3 and 4. So you can have that for example, to have 5 elements. For 3 elements, and you see here that these is just 3 parts here. So what is the difference to a list? Well, a tuple always has a fixed number. So if you define a type, the type says how many elements you have, whereas a list you can have a type, but there can be any number of elements in that list. Another difference is that a list always has to have the same type for all elements, whereas a tuple can have different types for the different elements. So for example, if you write like 3, high and 10, we get here a tuple where you see that we have an int, string, int, right? And this can then be used later on when you construct data. Let's see here. How do we deconstruct it? Well, there are special functions called first and second for tuples where there are only 2 elements. So you can, for example, if we define a tuple here that we call wow and 55, right? And then t, we can do like this. If we write first t, we get the first element of the tuple. If we write first second t, we get the second element. If we have a triple, so say that we had high 1 and 5 and do first, we get a type error saying that you cannot do that because the first and second only works for tuples which have 2 elements. So if you want to deconstruct things that are longer, you need to use some sort of pattern matching. And one way is to do pattern matching using the match construct. So let's define and look at this new tuple. Let's take a tuple again, and we say that we have wow, and we can do true there as well. We see that we have 3 different types here. If we want to match out this, we can actually, let's see here, let's do this and do another one. So we have 4 elements here. And if we want to match here, we can match on T and then and then we write the pattern, and the pattern looks exactly as you do when you construct in tuples, but you can use the wildcard if you want to ignore something. So if we just want to match out the string here, we just like this, and then we have to say that we ignore the rest. And then we just do like this, S. Then we extracted out the S. If we want to extract out, say, the 2 ints here, we can ignore this one, and then call this one x1 and x2. So these are then, as before, pattern variables. So you give them names and then you can use them later on. So now we know that both of these one were integers, and then we can extract it out and then, for example, sum them together. So you see that for this particular integer, for this particular tuple, we could then extract out this. So this match expression then works for any tuple here that has this type, a specific type here, which now happens to be this tuple. Okay, another way of doing this is that you can actually use a let to deconstruct. So you can do this with tuples because it's at compile time, we know how many elements and which types you have. So let's see again that we want to do this, then we can write the let. It's actually, you write the pattern to the left. So here, if say that we wanted to extract the Boolean value here, we can do like this. Equals to T. And we get, now we have defined B that can be used later on. If we can also have all of them here, x1, x2. And we have extracted out all the different values inside the tuple. Another way of doing this when you construct data is to use immutable records. So these are records where you can actually, you don't update values inside the records, but you just give them names. So it's very much like a tuple, but where you give different fields names. So let's look at an example. Let's go into the editor, because if you use records, you need to define the type of the record, and you just write type, and then let's call this person. And here we got a person type, and say that you have two fields, name, string, and you have to end that with a semicolon, and then age. Yes. Now we defined a person and the type of that person. And let's evaluate that, and we see that it says that we have a type, and the type looks like this. So it actually, in the type, it stores what is the name of these different fields. And then if we want to construct something, a record, let's say that we give this new construction a name here, P1, person 1, name equals to Sarah, and age equals to 23. We have a person, Sarah, with age 23. And if we want P1, we just get it. If we want to get out just the name, we write P1.name. If what we want to get out the age, we just write like that. And if I write something else, wow, it doesn't work because that field doesn't exist, right? So it can check that. Now, you cannot destructively update this, but we could, for example, define a new person. We can update this immutably. Let's see what happens then. Say that we have Sarah and age with this one, P1, but we want to change her age to 4. So then I can use this P1 with construct, and then I just say age is equal to 4, which means that it will return this person, but update it with just this field. So you see that we still have Sarah, but now age 4. But this did not change P1. So if we look at P1, it is still 23. So we just constructed a new record with this information. So if we want to, this new record, we can give that a new name, P2. And then we still have P1. You see here, we are not changing anything like in other imperative language where we're doing destructive updates. We are just creating new values, but we don't have to retype all parts of the record, but just update some of the fields. Okay, now let's jump into what's called algebraic data types. And this is pretty exciting and important. so say that you can use integers for many things, but sometimes you want to give names to things instead. Say that you want to have a new type, which we call country. And we define different countries here, right? Denmark, Germany, say China, USA. Okay. So we have now a new type where we can, it's a little bit like an enum in C. And each of these different elements are constructors. So we can construct now new data items like Denmark or Germany, and the type is country. And we should spell it correctly as well. Country. So let's evaluate the code. So we have a new type. And if I write Denmark, I get an element of type country that is Denmark or China. And we can use that and we can pattern match and so forth on it. So let's see here. Now, let's say that we want to create a function that is returning the country, country calling code for that country. So let's call that calling code country equals. So now country here this is a type, and here I just happen to give a name of a parameter with the same name, but they are not related, and we could call this parameter whatever we want, of course. So we do a match country with, and shouldn't do that, like this, and then we say Denmark, and you have to look it up, but I have done that already. So Denmark's got country code 45, Germany code 49, China got 86, correct, and USA got number 1. So I guess they were the first one to define this. Okay, so we have the country code, and let's check this. So that means that if I now call this function code and I write Germany, it returns 49. So we have created this data type that we can be used as a value, and then now we return different values depending on the what was returned here, like this. Okay. Well, what if we now added Sweden as well? What happens now? So now we see here that we have one country here, but we have Sweden here, but we have not added any matching. What happens if we call Sweden here with that? Let's just see what the compiler says here. Well, it gives a warning, not an error. It says that this pattern match is not exhaustive. So this is a really nice feature of OCaml, is that it checks that your pattern matching is complete. And it's very useful when you're refactoring code and so on, because it will tell you places where you have been missing, where you need to do the updates. But it's actually still a legal program. So if we do like this, we get the result. But now if we call with Sweden, we get a runtime error. So this warning tells you that you should actually fix it. But if you don't fix it, you get a runtime error. Okay, so let's fix that. So we have Sweden, and we know that that is code 46. And now we can call Sweden, and we get that, and we didn't get any compile time errors or warnings. Now let's say that we actually want to provide some more information with Sweden. We also want to say what is the population of Sweden, but we don't say it for any other country. We just happen to say it for Sweden. Okay, then you can add this kind of extra information for some of these types, and you use this off keyword, and after that comes the type. And now it's just one type, but we can have tuples, as we'll see quite soon. Okay, so you have this int here, and then we evaluate this, and now we should get an error, a type error, because it says that the constructor of Sweden expects one argument, right? Because we added an argument, but this one does not have an argument. So we need to fix this here, and we can basically just add that like this, stating that it's got one argument, and then you basically say the wildcard, but just please ignore it, and then it's fine. Right. Okay, so let's continue with this example. Well, we've said that this was the population, but giving it just int here might be not that easy to read. So what we can do, we can create a type alias. So we write population here, population equals int. So this is just a type alias. We say that population is the same thing as int, and then we can use this here instead. So this doesn't change the program. It just gives, if you check it, it's also okay. It just gives, it's a little bit more readable when you read the data type. So it's often when you read functional programs, these data types tells you a lot about the program. You see the structure of the program, and then you have functions operating on these data types. So let's try this out here again. Now we can call, define Denmark again, right? But when we do Sweden here, we cannot just do Sweden because it expects one argument. So we want to add something. And let's say the population of Sweden, now I write this in today's numbers. I mean, it changes all the time. I think it's about 10.3 millions right now. So we have defined now something of the population of Sweden, right? And that means that we can still call the calling code. Oh, we cannot. It requires this. So you need a parenthesis around this to be able to work. And since, just to see here, we will use, I use parentheses for this as well right now, but it's not needed. It's when you have tuples, this will also work right now. Okay. And now the next task is to create a function that extracts the population of the country. So please try to do that. Write the function now that extracts the population of a country, and let's call that pop just, and then country, and try to do that. And take a pause and then come back. And now we say that we have done that. So then what do? We do match on country with, and then you need to match on Denmark. Right. And what should we do with this? We could do like this. We could Denmark, should it match? What should we say about the population here? I mean, we don't know. So that's a little bit weird now. We have defined population here, but we don't have the population. So, but we need to return something. So let's, for now, we will fix this in a better way later on. But let's just say now, okay, Denmark is 0, and then we have Germany 0, and so forth. And maybe you recall from a previous lecture that you don't have to write this over and over again. You can actually write it like this. You don't have to repeat the end result there. And then you have China and USA and Sweden. We have the actual value. So let's just do that like that. We have the P, the population, and we return the population. And that's it. So let's see here. So if we say we can give this, let S equals to Sweden, right? And then we can write just pop S, and we get the population. But if we write pop Denmark, we get 0. Okay. Okay, can you write this in a different way? Yes, just to recall the shorthand notice, the way of doing is that you don't have to do the match, but then you have to use the last argument, remove that. So this is the same thing, right? Might be a little bit unclear to some people, but it's shorter. So yeah, you can do it. Do this in a way if you want to. But if we continue with this style, we can also actually, in this case, write it even shorter. So we do this Sweden here, P, and then we do a match all. So it's basically a wildcard. Anything that is not Sweden, we do it like 0. This will give the same result. The question is, why did I do this when you can do this kind of short form? Well, there is a benefit of repeating all this and really put this in. And that is because if I now add another country later on, this function will complain and say, oh, you forgot the case. And that means because maybe you don't want to do this. Maybe this new case, actually you want to treat it differently. But if you do it in this style, everything will be accepted. So in that sense, it's easy to add things, but it might be that you have then forgotten to do the right thing on this branch. So for larger programs, even if it's a little bit more tedious to write out all these ones, it's often recommended because when you're refactoring code, it's kind of more robust to changes. Yeah, so this was just defining some data structures, but these are pretty simple data structures with some constructor, and then you can stick on some data. But it gets even more interesting when we have recursive data structures. And what we're talking about here are variants, or also called algebraic data types. So these are types there you have constructors and attached data to it. So let's look at some new programs here. And now we have this, we will have can actually remove the populations part here, like this, but keep the rest. Let's look at a tree. So let's create a binary tree here. Type tree is equal to, and then we say that we have a tree with nodes. We have a node of tree. So here we have now a tuple, as you see with a star here. So we have 2 elements. And this is a node in a binary tree, but it refers to itself. So it's a recursive definition. You don't have to write direct here when you define the type. And then we say that we have a leaf in this binary tree with a string. So all the leaves include some information as string, but you can add any kind of information here and have more constructors and so on. Let's do that. And then let's define a tree. Just say, how do we construct a tree? Well, we just write the constructors. So first we have perhaps a node. And then that node should contain 2 things, X and Y, right? And we just replace this. Maybe we want to have a node there as well. And then we have a leaf, maybe. And the leaf contains a first. We say it's something called first. And then we have another leaf, saying second. Okay. We close that node. And then we have one more there. And let's put a leaf there as well. We call that a last. Okay. And we check that. Looks correct. And we evaluate. And now we have a tree. So we created this tree here, T1. And with just one tree, we can create other trees. Like can create a T2 where we just say It's just maybe T2 is less interesting. It's just a leaf. Right. So we can construct different trees now. And they are recursively defined, as you see, because you can have nodes inside nodes. Right, and you can draw this on paper as a tree, which makes it a bit simpler to view, of course. Okay, so now the next task is to write a function that pretty prints. That means that we are actually returning a string that prints all this information. So the interpreter here is kind of pretty printing for you, but say that you have a program you want to pretty print this in some other way, you need to create a string, a function that does that. So the task is to do that and let rec pretty, let's call that the function, and let's use this shorthand where we have a function. So that means that the first argument here now is the tree. So try it out and do that, and I'll give the answer now. So you could then pattern match, and you have to pattern match on the different things. So you need to add patterns for each of the things, each of the constructors in the type. So here you have a node, and you have to give pattern names for the two parts, left and right tree. Let's just write left and right here, and then let's do something with it. And we want to return now the string representation. So let's write node. Maybe we can use just to show that this is different from the ones generated. We do like this, and then we concatenate this with a recursive call to ourselves. Now we will pretty print the first node, the left node here. So we call ourselves, and that will return a string that will be then concatenated here. And we also add a comma just to make it look nice, and then pretty R. So we are pretty printing the right part of the tree. And then we end this. Okay, and then if we got a leaf, we maybe just say leaf with big letters, capital letters. And we can do like this if we want to actually get the quotation mark in here. So you have to back tick and escape it. And then S, and let's do the same thing there, like this. Okay, check. No, it was an error. See here, leaf. It should be called leaf. Okay, and now let's run that. So if we want to, we have this T1 here, right? And if we want to call and pretty print using our pretty printing function, we just call pretty and T1, and here we go. We get this, and you see the difference that we decided to pretty print and call it with capital letters here. Okay, nice. This is our first recursive function. Our next task would be to write a function that counts the number of leaves. So let's rec count leaves. So the task is to do that now. You want to count the number of leaves. You have to recursively go down and count the number of leaves. And pause. And now I will show you one solution. Left, right. Do that again. Count leaves, left. So this will recursively go down and count all the leaves in the left branch. And then we do the same things on the right branch. Right. So we are going through down, left branch, right branch, and then in the end summing it up. And the only thing we have to do here is also to then we can ignore the content of the leaf and just say that we have one leaf. And then we will recursively go down and up and count. Let's check it. And then we say count leaves, and we can do it for T1. And as we saw here in T1, we have 1, 2, 3 leaves, right? And we should get 3 back. Yeah, that's correct. Right. Now, let's say that we want to write this function that returns all the lists. So we want to append together. We want to create a list of all the strings that we have in the leaves. So we want to have a list of all this. We want to dive through the whole tree and just pick out all these leaves and put them in a list and return the list. Let's write this recursive procedure for that. So let's call that string list 1. And if you do that now, you need to think about how to do this, and try to now. We'll write 2 versions of this. One where you're using list append, and then one where we're not doing it, and then we'll discuss the benefits of and drawbacks of these approaches. So try to do that now. And pause. And now I give the solution. So we give a node, left, right. So then we want to append 2 strings. So we do a list append, and then we recursively call ourselves string list 1 left and string list 1 and right. So this means that we are recursively going down, and there we're also appending, and then we're combining everything together in the end. And for the leaf, we just take the string and return the string. Well, will this work? No, because list append assumes that there comes list. So we might need to put this into a list directly here. And this is called a singleton list. Right, so we try this out and see here. So string list 1, and we do this again for T1. And what we get is a list where we extracted out all the values from the leaves. Cool. Well, what is the problem with this? Well, list append is a little bit dangerous because it actually has to go through the first list when it's appending, and then before it can append. So it appends all these to this other one. So when we do this over and over again, we get a pretty bad complexity. So what we can do here is to write this instead using a accumulator pattern. So and then we kind of go through everything, and you will see that this really looks like a fold, but now we're doing it on a tree. In this lecture, we will not talk about how to do folds and maps and so on trees, because there are approaches to this, but I will not cover this in this first basic tutorial. So for now, try to write recursive functions over the data structures instead, except for lists where you should use the standard functions. All right, so let's do this and call this string list 2, and then we have a tree. Now we can just give it a tree. So we want to have this accumulator pattern, but let's do it with a nested function as we did in the previous one, so you don't have to provide this accumulator start value from the outside. So then instead we do this let rec work where we have an accumulator, and then we write function inside here. Okay, and now we do this node left and right. So what do we want to do now with the accumulator? Well, we want to call this work function because we want to accumulate, and every time we we want to recursively call first the left and then the right. And while we're doing that, we just want to go through down in the tree. So what we do then is to write work, and then in this inside here we just write work again. So this means that we first will do work on the left branch, and we'll just pass in the accumulator. And then we will do work on the right branch. So the resulting accumulator is given here to the second one when we do it to the right. And then in the leaf, we wanted to create a list, so we just append the string to the list using a cons in. Right. And now we just have to start off like this, work tree. What will happen then? We'll start off with an empty list and then traverse the tree. But as before, this will, doing this with accumulator, will reverse the order. So say that we want to have the same order, we need to also do a list reverse. And then I hit the wrong button here, like this, list reverse, and we got it. And it checks. So this list 2 now should do the same thing as list 1. We evaluate it, and we can try it out. 2, and it does the same thing. Right? We extract the elements, and we get the right order. So you can see here that we wrote it using a recursive pattern, and we got the same result. All right, so you can do a lot of things with trees. You can or other data structures here with when you define these with algebraic data structures. You can traverse the trees, collect information, update the trees. You change the trees, but you always return a new tree. And it turns out that still, if it sounds like this will be very inefficient, but the compiler will compile it very efficiently. So even returning new trees all the time results in very efficient implementations. Now let's look at this code again, this tree node here. What was this looks good, but we have now decided that we only have the same, we always have the same type here. It needs to be a string. Say that we want to make this polymorphic as well. So we want to say that, well, we don't want to decide here which tree we have. We just want to say which that we can have any value in the leaves. Then you type this by giving a type variable here. And then you need to provide that type variable in every place you use it in your recursively defined type. And here we then get the tree. So now we say that have this tree, but we can later on decide what is the actual type that we store inside the leaf node. This means that we can still have what we had here before. We can look at this. We can just copy this again. Like this. So if we run this, we get here, we see the leaf node, second, and so on, and it works. When we look at the tree here, we see that we wrote this type, and this is exactly what OCaml will say is the type with these type variables. But we can also here write another one. Let's T2, where we have, say, a node, and then a node, and then we give integers instead. I mean leaf here, of course. So maybe we have a node, and when we have a leaf, and 20, the leaf, 15, and then we add another, like this. if we run this again, you see here that we T1 and T2 are both using the same type definition of the tree, but we instantiate it with different values. So then if we now copy here the count leaves here again, and copy it down here. And actually we can remove some of these ones just to make it a bit. This. Remove this as well. Okay. Now we see this count leaves here. This count leaves is counting the leaves, but we didn't actually use this variable here of the type. So if we look at that one, we see that the count leaves has the type any. It doesn't matter if it's an integer or a string. You can take any of these trees and count the number of leaves. So we can say count leaves T1 is 3 and T2 is 3. So you see that now we have a polymorphic type, but also we can use polymorphic functions on them that works for any tree that has this definition, but this doesn't matter which kind of value. If we were using the fact that it was a string, then it will only work for trees that are of string. Now let's write another polymorphic function. So we want to now write a polymorphic function that has the following signature. We wanted to have it as like A to B, and then 3 to 3. So here we now want to have a function that takes a tree and updates it. So we wanted to update and change all the values inside this tree to be some other type or some other value. So it's kind of it's like a map where we are mapping and updating all the leaves, the values of the leaves. Let's define that function. Let rec update f, and we use this shorthand. So this is the second argument is now the actual tree. And please try to do that. See if you can figure it out how to do this function that updates the values of the leaves. And now I show you the result here. So we have a node. We just deconstructed and then constructed again. And we call update recursively down in the tree. And then we call update fr recursively on the right side. Okay. And then on the leaf, that's where we're going to do the change. So we have a value, and we just construct it again, but we apply f on it. And that's it. Check it. Run it. And let's do an update on T1. So let's say that we do update. We want to do an update on the tree T1, and we write a lambda here. We say that x is now the element, so it's for T1 it would be the string, and we say that we add, for example, this to the string. Let's see here. What did go wrong? This type has type string tree, but an expression was of this way more complicated format. Let's see here. What did I do wrong? Well, you see, I happened to write twice. This was the mistake here. See, here we go. Now, you see that I was updating this tree, and everywhere we added this dash dash to the leaves. And this can be an arbitrary big tree, of course. And we can do the same thing. I mean, if we apply this to T2, it will say that it's not compatible because T2 was defined with integers. So let's write another update function where we do something with the leaves and say that we are just adding a number to it. See here. Update fun, and we forgot the X there. And we're just adding the number like T2 had originally been that. You see here, we are returning a new tree. We are not changing anything. T2 is still got the value. We were just returning a new tree where we update. So we always transform and create new trees. We never update the trees themselves. Okay, that is enough about the trees. You can do it. Just play around and try out different examples with these trees. The last thing I wanted to show you was what is called option types. So we saw that this problem that we had here before with the option types was that you could not extract out the values here from country code. When we wrote that this pop function, we return 0 all the time, right? We return for Denmark, Germany, and so on. We got the value 0, but the population of Sweden we could extract out. We do not want to do that. I mean, it's kind of strange to say that the population is 0. So we actually want to say that either it's okay, here you got the population, or oh, we don't have the population. And this is where you can have this option type, or sometimes called the sum type. And this we can look at it in the top level here to see. Just clear out some. So an option type has two possible values. Either it's none. You see, this is the option type option, and it's got any kind of type containing it, because the alternative is that you have some, and that is then you provide the value. You have some, for example, it says that, oh, you have a value and it's 10, or you have none. So you either, an option type is either some, you have the value, or none, you did not have the value. And this sum is polymorphic, so you can use like for strings or whatever type. And then it says in the type here that the option type here, this is an option type of type int, and this is an option type of type string. And this part is actually stating what is the type that is constructed. So you see here, the option type is actually just an algebraic data type that we could have defined ourselves, but in the OCaml documentation and in the standard library, these option types are already defined. So it's kind of standard to use them. Let's use it here just to again then rewrite the pop function here, but return the population, that is extract the population, but just return the value of the population if it is Sweden. For all other cases, we should just return none. And we can do that just like this. Let's now write the proper China and USA. And instead of 0, as we had before, we return none. And for Sweden, we return some and then give the value P. So if we evaluate this, if we write pop Germany now, we will get none. If we write pop Sweden, and we have, say that we just had 100 people in the country, it returns some. And you can pattern match on this. So typically you return and then you do different things depending on what kind of value you have on that. So say that you wanted to print the population, and you call pop and you get the population, and then you want to print the value. You say that we are using this library, printf. We can open this, and then we can use this without. We can also write it directly with a dot notation that we did before, but we can also open a module. So let print pop function. We have one argument there and none. So now we just said if it's none, maybe we want to just write out population is not available. Okay, and for some value, we basically say just what is the population. And the printf here is very similar to you know C and standard C printf, and then we write. Okay, so then we'll print out, either we'll print out there is not available, or we will actually print it out, and we can do whatever. So it's just that this is a good way of doing error handling in a functional way. You're returning either it went okay or it went wrong. And then you evaluate this, and we got an error. We forgot something. We forgot to say that printf here. Here we basically say that, oh, we should provide something to print, and we forgot to do it. And the compiler is smart enough to discover this, so that we forgot to add v, because that's what we are printing. Right. So if we then write population, and we got this to Sweden here, say Sweden 100, and then we do like this, and then we do print pop, and it prints that. We can actually also show you the pipe operator here. Instead of nesting it in this way, we can actually send the result to the next operator, print pop. Okay, and if we repeat this, but we take Denmark instead, it will print population is not available. Great. This is basically what I wanted to show you about algebraic data types. So we've just shown this on very small examples, but I mean, in the course that this is designed for, we are going to write a compiler, so you can do this, you know, have arbitrary complex structures when you operate on trees and data structures. So I hope you got the main points of this, and thank you for listening to this video. In the last lecture of this introduction, I'm going to show you a little bit about you know, exception handling. That is some more things about side effects, some things about exceptions, and also about basic I/O input output, so you can get started to write actual programs. So thank you for listening. Take care.